Okay, let's look at some background physics so you understand what's happening behind the scenes. The idea is this: if you have an object that is moving in a circle, it's going to take a sideways force to make it move in a circle. The reason for that is Newton's first law of motion is that an object, if there are no forces acting, it's going to tend to move in a straight line at a constant speed. If I apply a force to it in the forward direction, it'll cause it to speed up. If I apply a force in the backward direction, it'll tend to make it slow down. If I apply a force sideways, like this, then it's going to cause it to curve. So you can think of it as the little change in velocity is this direction. And so it started off going this way, and now it's going this way, all right? Now, this force has to be purely perpendicular, and that's easy to understand if you think about it a minute, because if there were any component of that force that were in the forward direction, it would cause this thing to speed up. And if any component was in the backward direction, it would tend to slow it down. So in order to curve the path so that it's flying at a constant speed but in a curved path, the force has to be purely perpendicular. And if it's in a circular path, it's the same curvature everywhere, so this force is going to be a constant. So this force, which is pointing toward the center of the circle, is called the centripetal force. So that's the force toward the center. Now, how much force is involved? Well, that depends on how much mass we have here, and it depends on the speed, and it depends on the radius of curvature. And the relationship, it works out if I'm not going to do all the derivation here, but it turns out to be mass times velocity squared divided by r. And that's going to give you your centripetal force. That's a C there. Okay? So, the centripetal force, the force needed to bend the path into a circular arc, depends on the mass of the object, the speed, and the tighter the curve, the smaller the radius, the larger the force has to be. Okay, so making the numerator big makes the force big. Making the denominator small makes the force big. Now, Newton's second law says F equals ma. So all of this that we've been saying about the force can be translated to a simpler comment about the acceleration. This force leads to what's called a centripetal acceleration. And just take the force divided by the mass, and that gives us the acceleration. So if I divide this by the mass, instead of this being a force, that's now centripetal acceleration. And this is what GeoGebra is going to calculate, all right? Let's see how this applies to the banking angle. If this is a plane, in order to fly in a curve, it's the wings that have to provide the centripetal force. So there has to be a sideways component of the lift from the wings in order to pull it into a circle. And in order to get that sideways force, you need to bank the plane. So the wings are partially lifting inward as well as lifting upward. Let's take a look at that. So I'm going to do two pictures here. If here's our plane flying normally, we have gravity acting downward, but what the plane has to provide is lift in this direction. Okay. If it's going to be flying in a circular arc, it has to be tipped. And so now here's the plane. I'm imagining the plane is flying directly away from us, and the lift on the wings is going to be in that direction. Okay, I'm going to draw a slightly larger diagram here. This lift is going to be doing two things simultaneously. It has to provide some upward force because it still has to balance it against gravity, but it's also going to be providing a sideways force in order to cause it to go around in this circular arc. And so if I combine the two, the upward force combined with the sideways force results in something of a net force like this. And if I break it down, we can see a couple of triangles here. And so that's the direction that's going to seem like it's up. If you're in the plane, it's going to feel like you're pushed this way. That's the reaction to this force, but the lift is providing a force over here. Notice that's perpendicular to the wings. It's the wings that have to provide that force in this direction. Okay. Now, we want to calculate the tip of the wings and see how that relates to our acceleration. So let's take this angle here and just call it B. That's going to be our bank angle. That's the angle of the wings from the horizon. That's also, I think you can see, it's going to be equal to this angle. It's the angle between the tail and vertical. Why is that true? Well, look at this angle in here. B plus that angle adds up to 90 degrees. But this angle plus this angle adds up to 90 degrees as well. Okay, so these have to be equal. So let's look at this triangle. And what do we have? This is the force that's counteracting gravity. So it'll be the force of gravity, and here's your centripetal force. Okay, and so those form a right triangle. And if you know any trigonometry, measuring from this angle down here, that's the opposite side. And this is the adjacent side. This one is called the hypotenuse, okay? And the opposite over the adjacent is the tangent. The tangent of B is going to be F sub C over F sub G. And we saw earlier that if I divide by the mass, I get accelerations instead of forces. I could go either way. But the mass basically is irrelevant. It cancels out. So let's just do that. So that's the same as acceleration centripetally. And this is the acceleration of gravity, which is just called G, by the way. And if you express the centripetal acceleration as so many G's, like let's say, for instance, 3 G's, we now have 3 G's divided by G, cancel, cancel. We have a number we can plug into the calculator and figure out this banking angle. So the tangent of the banking angle, whatever it is, gives us 3. The inverse tangent of 3 would give us the banking angle. So let's look at that. Okay, pardon the fancy calculator. Ignore the top row. Everything's going to be in the bottom row here. So if I put in a 3, and then I say I want to know the angle that's going to give me 3 as its tangent, that's finding the inverse tangent, or ATAN there. So I go orange and hit that. Notice that's going to give you a 71 degree, 71.5 degree roughly. That's going to give you this kind of a banking angle in order to get 3 G's. By the way, just for reference, if you're on a ride at an amusement park that gives you a sustained acceleration of 3 or more G's, you're going to have people that are going to start blacking out. I was on a ride that was something like that, and I started getting black spots in my vision. So this is a lot of G's. The plane is designed to only go 2 point something G's normally, and 3 is probably sustainable. But once you start getting much above that, you're putting the structure of the plane at risk. Okay, bottom line, we're going to be looking at arc curvature, and the arc is determined by the radius, and then we're going to have the velocity, and from those we're going to get the centripetal acceleration, or I'm going to call it lateral acceleration. It's the sideways acceleration here. And from that, we're going to evaluate paths that give us reasonable values for these. By the way, notice that even if you could survive a 3G bank, you're going to notice, observers on the ground are going to notice a 71 degree banking angle, definitely. That is very, very steep and unusual for a plane. So you're not going to get sideways accelerations that look like this unless you have every observer out there on the ground saying, look at that weird plane doing a huge bank. That was not observed. So big accelerations are unfeasible dynamically, even accelerations like this are going to give you banking angles that couldn't help but be observed. Okay, let's go back to our primary video now.